Okay, so we would like to show Helder's inequality. This is the following, that if we have two real numbers, P and Q, that are greater than 1 and satisfy the equation 1 over P plus 1 over Q equals 1, and A1 up to AN, B1 up to BN are any real numbers, then we have this inequality. So the idea behind this is to consider, so let's say proof, is to actually do a normalization. What do we mean by this? So first of all, note that if sum from k equals 1 to n of ak to the p is equal to 0, or sum from k equals 1 to n of bk to the q is equal to 0. If one of them is 0, then there is nothing to prove. Why? Well, take, for example, the case that this is true, that the sum of the absolute values of the ak to the p is equal to 0. Then that means that all the ak's have to be equal to 0, which means that the left-hand side of the inequality is 0. And so no matter what the right-hand side is, the right-hand side is also 0. It's correct. So we can assume that both of them are non-zero. So we may assume that both of these are positive. And this means that we can do the following little trick. Notice that the inequality is homogeneous both in A's and in B's. So it holds for A1 up to AN and B1 up to BN, if and only if it holds for lambda A1 all the way to lambda AN and mu B1 all the way to mu BN for some lambda comma mu that are greater than 0. Okay, now ask yourselves why. And the answer is that if you write the inequality with the products instead of the original numbers, then exactly because of the fact that we have pth powers and then we take the pth roots, this is equal, so this, I'm sorry, this inequality is equivalent to lambda mu times pretty much the inequality that doesn't have the extra factors. Oops, we said without the extra factors. This is actually a quite classical trick for these inequalities that can be called homogeneous. And pretty much you can now, since we're talking about two positive numbers, you can cancel them. And that shows you that the original inequality is equivalent, or rather the inequality with the products is equivalent to the inequality without the products. Sorry about this. This should be a Bn. Okay. So the question is, can we use those factors judiciously so that we get something which is useful for us? And the answer is yes. And pretty much what we do is we take lambda to be 1 over the sum of, from k equals 1 to n of ak to the pth to the 1 over p power, and mu to be 1 over that, because the interesting thing is the new numbers that we get, for which we have to show the inequality, satisfy what? I mean, if we take the sum of the AKs over this number right here, and you raise this whole thing to the pth power, there is a very nice cancellation, which gives you pretty much sum from k equals 1 to n of ak to the p over this, which can now become a common factor in front. And every time you have numbers and you divide them by their sum, then the new sum is simply equal to 1. And that will be true for the bk. So this tells you that it is enough to show the inequality in the case that, oops, sorry about this, that sum from k equals 1 to n of ak to the pth power is equal to 1, and sum from k equals 1 to n of pk to the pth power is equal to 1. So it's enough to have these conditions because of the homogeneity of the inequality. So now, once we assume these two conditions, everything becomes really straightforward, because what we have is that A1, B1 plus AN, BN is less than or equal to A1, B1 plus AN, BN by the elementary properties of absolute values for real numbers. And of course, this would have been true for complex numbers as well, but we're simply interested. And now, apply the Young inequality to each of these products. So we will have that the first product is less than or equal to A1 to the P over P plus B1 in absolute value to the Q over Q, all the way to AN to the P over P plus Bn to the Q over Q, which is the same thing as A1 to the P plus all the way to A sub n to the P over P plus B1 to the Q plus Bn to the Q over Q. And we said that each of these sums is 1. So this gives us 1 over P plus 1 over Q, which is equal to 1, which, by the way, now the number 1 is precisely equal to the product that we wanted to consider. And that's all. Okay, so we showed the inequality in the special case because of the argument that we explained before. It's true in the general case. And actually, the truth is that one could have started with the original inequality and divide pretty much the left-hand side by these two quantities, match the ANs with the first one and the BKs with the second one. But I think it's useful to remember this general fact that is, if we have inequalities that we can spot they're homogeneous, that we can apply such an argument. Okay, one way or another, the essence of the argument is the same, and it all follows from Young's inequality, which again we should record as for non-negative numbers, AB is less than or equal to A to the P over P plus B to the Q over Q. Again, this is shown in a separate video. And that's all. Thanks for watching.